Today we're going to use Mathematica to graph secant lines, and we want to use that to help conjecture equations of tangent lines. Now, if you haven't worked through the intro to Mathematica that I have, that would be very helpful to go through that. And also we're going to use the outside-inside style of writing, which helps keep up with parentheses and braces, commas, etc. And this is lab 2.1.1, rates of change in tangents, for our Calculus Mathematica manual. And what we want to do here firstly is we want to take this function f and we want to graph 5 secant lines, and we're going to use the difference quotients with different corresponding h values. We have a list of them here, and from that we're going to see if we can get a possible trend of slopes to help us derive a slope of the tangent line so that we can come up with an equation of a tangent line. Now, we have to remember something from algebra, so I'm going to make a note here. I'm going to use Alt-7 as a hotkey to insert text. That's a very helpful thing to remember, and we're going to recall how to find the equation of a secant line. We use algebra. We say y equals, we have some sort of slope, and then we need a point A plus the y coordinate has to be on our function f because the secant line crosses through our curve. So we're going to pick a point A, f of A, and then we use the point slope form from algebra to figure out the equation of the secant line. Now, how do I know this is a secant line? Well, it depends on what the slope is. So we say where the slope is my difference in my y's, and the difference in my y's is going to be f of a plus h minus f of a. H just represents a short distance in the x direction away from my initial value a. So that's my difference in y's. My difference in x's would be a plus h minus a, and if you notice the a's subtract, we just end up with h, and that is the difference quotient. The difference quotient gives me the slope of a secant line. Now for these first two exercises, we're going to have a list of h values that we're going to use for both exercises, so I'm going to go ahead and make a list called h that I can use for both of them. Okay, now for exercise 1, let's go ahead and define our function here. Alright, now if I just plotted f of x to kind of see what we have some sort of parabola like this, and what we're interested in is what's going on at 2. We want to get an estimate of the slope of the tangent line. The tangent line is going to be the line that just hits right at 2 and bounces off, and the idea is that the slope of the tangent line kind of mirrors the, I guess we'd say the slope of this curve right at 2. A more technical way of saying that is the instantaneous rate of change at 2. So there's my graph. What I want to do though is be able to graph 5 secant lines right there at that point. Okay, so in order to avoid having to just characterize these over and over again, I have an idea. I'm going to make a function called Secant Slope. And what I'm going to put into Secant Slope is an A and an H. And I'm going to define it just like we did in our note at the beginning of f a plus h minus f of a all over h. And now this way, all I have to do is put in values of a and h and I can get the slope. If you've never defined a two-variable function before, I can list the variables in my function here. Just make sure you put an underscore for each one of them. For example, if I had left out the h, notice here that my h's are a different color now. So I need to put in h, and notice when they're green, that's telling Mathematica that those are all variables in my function. So there's secant slope, and we could also make a secant line function that needs 3 variables, a and h, and then x as well. So that way we can plot it. And the secant line is going to be the same thing that we set up here in our note. It's going to be secant slope, and I have x minus a plus f of a. There's my secant line. Okay, so now I've defined slope and secant line for any values of a and h that I want. In particular here, our a value is going to be at x equals 2. We're going to put in 2 for a. Alright, now before we actually get into our exercise, let me show you a brief illustration of why the secant line is helpful, or why we're doing this, why change these values of h. So I'm going to put in this manipulate of a plot. Don't worry about all the details here, that's okay. This is what I want you to see is the graph. The blue is our function, it's our parabola. In the yellow, this is a secant line for a specific value of h. Now in my code I changed that to k, and in particular this is k equals -3. Okay, now as I get my k value closer to 0, notice here that the secant line is dragging across. And what I mean by dragging across is that the point of intersection with the blue curve is moving over closer and closer to where we intersect at x equals 2. And as I get closer and closer, notice when I get really close to 2, and my k value or my h value is getting really close to 0, that looks like a tangent line to me right there. And this is with a k value of 0.01. And so if I can find the slope, if I can find some sort of pattern in the slope of these secant lines as I get closer and closer to this, then maybe I can guess what the slope is exactly at the tangent line. And we have to do it this way, at least at first, because the slope formula here, if h is 0, that's not going to make any sense. Okay, so that's the idea. We're trying to find a pattern as h gets close to 0 of the secant slope, and we use these secant lines to do it. All right, and this illustration, I think, is a good illustration to kind of give you the idea. Now, what we want to do is we want to plot f of x like we did here, but we want to do it with the secant line. So, for example, if I was going to do one secant line, I could put in a list of functions because I'm plotting more than one function, and I'm going to say secant line, we have an a value of 2, let's have an h value of 1, x, like that, and we're going to go from -4 to 4 again. Okay, there it is. There's my secant line. Now, I wanted a nice box, so I'm going to put aspect ratio to be 1. That makes it square. Okay, so there's my secant line. But I need all 5 of them. So I guess I could go out and list secant line, secant line, secant line, secant line. An easier way to do that is like this. I'm going to make a table. And so notice I open and close my braces immediately. That way I can keep up with what I'm doing here. Of secant lines, each with an a value of 2, an h value, and an x. And what I want to be able to do is somehow let my index go through the h list. What I mean is when h is 1, which h is 0.5, 0.2, etc. And the way I can do that in Mathematica is if I do double brace around h and put in a number, let's say I, if I put in 1, for example, that's going to be the first item in the h list. So if I say I'm going to let the ith item in my list, I going from 1 to 5, because we have 5 things. And this is different than a lot of computer science languages. They'll start with index 0. Mathematica is starting with index 1. There they all are. There's all 5 secant lines. Okay, now it looks like a mess because they're all the same color, and the way you can get around that is just a little trick with your plot. Just put evaluate around your table, and now it kind of evaluates, it plots each one of them separately and gets you this nice rainbow thing. Now if you want to get a little closer to what's going on, instead of going from -4, how about we just go from like 1 to 4. Alright, so there's that part of the parabola, and you can see all these different secant lines. Does that make sense? Okay, now, does that really help me get an idea of what the tangent line's doing? Maybe not. It's kind of a little bit of a mess, but what I can do is say, let's take it secant slope. We have a value of 2. We're going to go through our entire list of h. So all I have to do is type in h here. I don't have to do a table or anything. And there, these are the secant slopes. So I'm going to put a comment in here that says, we're going to evaluate secant slopes for each value of h in our list. We got those. Now, judging by that, it looks to me, I'm going to hit Alt-7 for a comment here. So by my observation, or let's say by observation, it looks like the secant slopes trend towards what? 1 as h gets close to 0. So that would tell me then that I think that the tangent line appears to be y equals, we need a slope. We just said we think our slope is going to be 1 times x minus the point 2 plus f of 2. Okay, now we can use some algebra here. We can use the simplify function on that. Let's say 1 times x minus 2, which we know is just x minus 2, plus f of 2. Let Mathematica do the work for us. there it is. So I'm going to leave one more comment that says the equation of the tangent line appears to be y equals x minus 8. Let me go in the graph real quick, and let me just take out this evaluate just to see if that makes sense. If I just type in x minus 8 as the second function, wow, that looks like the tangent line to me. So I think this trend kind of led us in the right direction. So if I had a guess, I'd say the instantaneous rate of change right at 2 took on the value of 1 based from our secant slope trend. Okay, now we're going to do the same thing for exercise 2, but this time we're just going to change our value of f. And I don't usually like using the same name of a function more than once in the same document. We already used f, and I'm going to reserve g for exercise 3, and we've actually already used h as well. So we're kind of down on the list a little bit. I'm going to do k of x to be 3 square root of x. Sometimes if you double up, like you redefine f, most of the time it's okay, but sometimes your memory kind of gets stuck, and it can just be kind of frustrating. Now, for some of this, I'm just going to copy what we've done already. I mean, why make it harder on ourselves? Come down, exercise 2, paste them in, and I need to adjust a few things. This is k, not f. Same here in my secant line, and I need to evaluate both of those. And then on my plot, I'm plotting k of x, and secant line, my a value has changed now from 2 to 4. And I'm still going through the values of h, and since I'm going around 4, let's go from 1 to 6, and we can adjust that if we need to. Let's see if we did this right. Wow, okay, so we have the blue line is kind of this curve. It's a subtle curve, and then you have all those tangent lines kind of jumbled up around it. Let's zoom out a little bit and make sure we can see what's going on a little better. If I go 0 to 10, that shows the kind of the dramatic bend in the curve a little bit more, and all those secant lines are kind of bundled up right on top of each other, but they do seem to be close to what we would think a tangent line would be right at 4, which is kind of what we want. Alright, so the question then is, I mean that was the plot, but now we got to guess what the tangent line is, what the equation of the tangent line is. I'm going to do the same thing we did earlier. We're going to do secant slope. We have an a value of 4, and we're going through h. And let me leave my comment again. We're going to evaluate secant slope for each value of h to approximate the tangent slope when h equals 0. Alright, so when I hit Shift Enter there, at first I get an exact expression with a square root of 5, but after that I get some decimals, which kind of actually helps me out a little bit more here. And if you wanted that to be a decimal as well, you can just put an n around your function, and it'll give you decimal values for everything. So there we have our decimal values, and by my little eye, it looks like this is getting closer to 0.75. Alright, so Alt 7, by observation, it appears the tangent slope is 0.75. And so the equation of the tangent line is going to be y equals our slope, which is at 0.75, and our point, which is going to be, we had an a value of 4, so x minus 4 plus k of 4. If I let Mathematica do the algebra on that, which we could do ourselves, just being kind of lazy, honestly, but that's the power of Mathematica, letting it do it for us. Alright, we get 0.75x plus 3, so Alt 7, the equation of the tangent line appears to be y equals 0.75x plus 3. Okay, now like last time, let me just make sure that that makes sense. 0.75x plus 3 we said. And I mean that looks like it. Let's get really close around 4 just to see what's going on. So how about like 3.5 to 4.5? What do you get? You can barely tell the difference between the blue and the yellow, right? So the yellow is the slope of this yellow line, hopefully you can see, is a pretty good model of the rate of change along the blue line. That's the whole point of the tangent line. Alright, there, I zoomed out again and put the table back because it looked nice that way. Alright, and so there's our answer. And I hope this makes sense, and I hope, even though you're learning two things at the same time, okay? You're learning the calculus, and then you're also learning the syntax and getting your feet wet with Mathematica. try to keep those two concepts separate so you don't feel like you're just caving in on yourself. Let the calculus be the calculus. Understand what we're trying to do with secant slope and the trend of those slopes to help us find the equation of a tangent line and what that means. But then also look at how we're doing this with Mathematica. We're defining functions, we're doing a plot, and we did a table, which is kind of weird. That's okay. You don't have to know how to do that quite yet. We'll get into that more. But hopefully you can see how Mathematica can be useful in tackling problems like this. Okay, let's look at exercise 3. So here, this time, we want g of x, which is this negative 2x plus 1 times 3 minus x. All right, and we also want d of x to be, well, it looks like the difference quotient of g, right? This is the difference quotient with a particular h value plugged in, 0.001. And notice that 0.001 is very close to 0. So this is kind of like a function that for any particular value of x gives you the slope of the tangent line. Let's see what happens when we graph these two things together. So when I plot, I have to make a list, and notice I am opening and closing brackets and braces one after the other because it just makes it easier to keep up with things. And we want x to go from, I don't know, let's go from negative 10 to 10, and we can adjust it as needed. Okay, that looks pretty good. Now I'm going to add a few things just to make it look more appealing. Plot style changes colors and thickness and things like that. And because I have two functions, I need to list them out. So I'm going to use directive. This would be for the first function, and directive again, this would be for the second one. So for the first one, how about let's make it red and thick. And for the second one, how about, I don't know, orange and thick again. And we can make the dashing small. All right, how about let's change the aspect ratio again to 1. And that just makes it equally wide as it is tall. And let's take the ticks off. That means that the axes will not be labeled. Let's see what we get here. Yeah, I like that. Okay, that almost looks like a textbook image, just the way that looks. Okay, so now we want to look at, try to think of the relationship between these two functions. You have this red function and this dotted line here, and they are related somehow. Now it's not as obvious, but if you think about it this way, look at this dotted line. It hits the x-axis kind of right in this spot right here. So while the dotted line is below the axis, what is the red curve doing? While the dotted line is below the axis, it looks like the red curve, as I'm going from left to right, is going down. It's decreasing. When it hits the axis right here, it looks like this red curve kind of bottoms out for a little bit. And then notice when the dotted line is positive, when it's above the x-axis, going from left to right, what is the red curve doing? It looks like it's going up. It's increasing. And I think that's the relationship. Okay, so remember, this d of x is the difference quotient, which is the slope of the tangent line or actually the slope of a secant line at any value of x with a very, very small value of h. So it's almost 0. So it is almost the equation of the tangent line. It's almost the slope of the tangent line for any value of x. So if I'm having a negative value here, that means that the curve has got negative values of tangent lines. So it's got to be going down. And if the dotted line is positive above the x-axis, that means the tangent lines for this red curve there will have positive slopes. It means it's going up. And I think that's what we kind of want to say. So we're going to say we observe when d of x is below 0, g of x is decreasing. And when d of x is positive, g of x is increasing. This makes sense to us since d of x gives a close approximation of the slope of the tangent line of g of x for any particular value of x. So when those tangent lines have negative slopes, g of x has to be going down. Alright guys, this is our first lab. I hope it makes sense. If you have any questions, I'd be glad to help with the Mathematica, with the concepts, with the calculus. I'd be happy to help. Just leave a comment or get in touch with me. I hope it makes sense. Just keep working at it. It'll slow down for you. and thanks for watching.